So we're going to start with number 8 here. Garden store in the summer, you lift a bag of fertilizer with this force, it moves upwards with this acceleration. What's the mass of the fertilizer bag? How much does the fertilizer bag weigh? Okay, so this is number 8. So I start by writing number 8. And then in this first section, I am doing my force diagram, which, let's see, I'm going to draw my bag of groceries. I'm not a great artist, so there's my bag of groceries. And I know that it's on Earth, so it's going to have a weight on it. And then you apply some force on it to lift it upwards, and it's accelerating upwards. So there is the force diagram. That is your Y. Let me say it again. That is your Y for this problem. No, that's just a force that you applied to it. A generic force. Remember, there's that key to what those terms stand for on the top of the sheet that we did, full packet we did yesterday. This sheet has some extra things on it that you'll learn about next time, like free body diagram and such, which you don't really need to worry about, but they are actually on the sheet, and we'll go over those tomorrow. But I'm going to work directly from here, and so I'm going to work in the how here. You can forget about that word free body until tomorrow. I have my one equation. Some of the forces, in this case, they're all in the Y direction. Case of Y. I have two forces. Which way do you guys want to call positive? Up. Okay. So I have two forces. I have a positive F plus a negative F sub G that points downwards. And that's going to give me my mass times my positive acceleration because it points upwards. Huh? I haven't put any numbers in yet. I've just written characters, variables. My next step will be to either put in numbers or rearrange algebraically. Which would you prefer I did? Put in numbers, okay. Good, okay. You got it. So I've been requested to put in numbers yet. Let's see, you lift a bag of fertilizer, the force used 127 newtons. So that's that F, 127 newtons. And it moves upwards with an acceleration of 0.760 meters per second squared. So that'd be that minus F sub G equals M times, and this was 0.076, 0.760 meters per second squared. All right, so there are the numbers in. All right, good. So now I need to solve for, first thing to ask me is what is the mass? So I should probably look at my equation sheet and notice that I have this equation here that says the force of gravity, or the weight, is the mass times the acceleration times, the gravitational field strength, little g. Yep, they are. And they're online. Little g, if it has units of meters per second squared, is the acceleration due to gravity, so the acceleration in free fall. It's also the same value as the gravitational field strength, which is in units of newtons per kilogram. So you can kind of use them interchangeably because they're actually the same units. It's still 9.80 and it's still directed downwards. Okay? And if you look at the bottom of the equation sheet, oops, wrong one, sorry. They're in the back and they're also up online. If you look at the bottom of the equation sheet, On the back side, you'll see that it's listed both ways with equal signs between it. Okay? So I'm going to substitute that in now. Let's see. So I'm keeping my numbers in here. 127 newtons minus m times little g equals m times 0.760 meters per second squared. Yes, the weight, F sub g, is m little g. If you look on the equation sheet, and you look at the forces box, now this is the honors one, just because I already had it up. Your forces box has just moved up a little bit. You'll notice the equation for the weight. Not really the equation, the identity of the weight. There, right almost in the middle. You see it? Right, exactly. That would be the equivalent of weight, yep. Hi. It's in the top drawer, way near the back, and it says CP equation sheets on the folder. The honors ones would be the file just beyond the CP ones. The CP ones are just simplified versions of the honors ones at this point. And I know they're in there because I made sure that there was like 50 of them this morning. Should have a front and a back. If you just get a front or just a back, you took my master copy. Okay? So now I need to, well, you probably want me to put in numbers again, so I'll put in numbers. I'm going to ignore this free body stuff here. Just keep working. 127 newtons minus m times 9.80, point there, newtons per kilogram equals m times 0.760 meters per second squared. I only have one variable. I have m. That's what I would want to solve for. So I'd want to get those on the same side. And so I'm going to rewrite this as 127 newtons equals m times 9.80 newtons per kilogram plus m times 0.760 meters per second squared. And now I'm going to factor out my m's. Because I'm assuming this is taking place on the Earth, and so I looked at the equation sheet, and all the way down the bottom of the second page, and I know, and the gravitational field strength on the Earth is 9.80 newtons per kilogram. Yes. Yeah. No, because when I take something that is negative on one side and it's addition, and I move it to the other side, it becomes positive. Because to get it from one side to the other, I need to add it to both sides. Let's take a more simple example. Okay. You know, sometimes when especially when we have numbers and variables mixed in, simplify it and see if it makes sense. All right. You good then? Okay. My next mathematical step here would be to factor m out of both of these. So I'm left with 9.80 newtons per kilogram plus 0.760 meters per second squared. Now, newtons per kilogram and meters per second squared are really the same units. That's why we can add those two together. So I'm left with, let's see, simplifying a little bit more, 127 newtons equals m times, let's see, 9.8 plus 0.76. 9.8 plus 0.76. said enter 10.56 times 10.56, and I'm going to stick with meters per second squared. I can pick either one. Actually, I'm not going to stick with meters per second squared. I'm going to write it as newtons per kilogram. Well, because I think maybe more people, when I do the next math step, will see why I come out with kilograms. Yeah. But you're right, they're exactly the same. So my next math step is 127 newtons over 10.56 newtons per kilogram equals M. And so M equals, time for my calculator again, 127 divided by that one, and that one, 12.0 looks like to me. 12.0 kilograms. So that is the mass of my shopping bag. But then they also asked me what's the weight of the shopping bag. And I know from my equation sheet that weight is m times the gravitational field strength. So the weight of my shopping bag is going to be my 12.0265 kilograms times 9.80 newtons per kilogram, and get F sub G equals, nope. So if I multiply that by 9.8, I get 118. 118 newtons. Hopefully those are correct. Let's see. 12 kilograms and 118 newtons. And they are. All right, so we're going to go on to number 6. And how much tension must a rope withstand if it is used to accelerate this car vertically upwards? Oh, this is going to be like very, very similar to the last one we just did, except they told us the inertia, the mass of the car, rather than telling us the force that's used and asked us to find the force. Cool, this will be like reinforcement. So let's draw our force diagram. This is number 6. So our force diagram, there's our car. Again, we'll put wheels on it just to make people happy. There is the weight, always downwards, towards the center of the earth. You're pulling it up with a rope, so there's a tension force. And we're told that it is accelerating upwards, I believe. Right? So it's accelerate vertically upwards at this. So good. And then, you could always add in, a lot of people do this on the car, label it that it has mass M. That's kind of an optional thing, but it can be helpful to remember, especially when we get to systems in about a week, and we have multiple things in here rather than just one thing. Okay? So, there's my force diagram, which is my Y. And I'm going to go down here and, hopefully not a surprise at this point, start with my only equation, which is this one. And it's in the Y direction, so it's just Y. Looking at my diagram, I have two forces. and one acceleration. Which way do you guys want to call positive? Up, okay. So we have the force of tension up, so I make that positive, minus the weight down equals the inertia times that positive acceleration. A is up. So I'm going to rearrange that a little bit before I put any values in. So I'm interested in the tension, so I'm rearranging that so it's by itself. I can do that by adding the weight to each side, right? And then from last time I know that the weight, and from my equation sheet, that the weight is mg. And now I think I'm ready to substitute in numbers. Force of tension, my m, I'm told, is 1,800 kilograms. 1,800 kilograms. My acceleration, I'm told, is 0.5 meters per second squared. That's going to be that plus mg, 1,800 kilograms. That's my mass, and my g is 9.80 newtons per kilogram. So in both cases, I'll end up with newtons, and I have all numbers. Do a little calculator magic. Clear that. 1,800 times 0.5 plus 1,800. Is it 1,800 or 18,000? 1,800. Okay. 100 times 9.8. I get 18,540. So 18,500, rounding to 3 sig figs. Let's see if I got it right. 18,500, rounded to 3 sig figs. It was 18,540. Yay! So we're just going to do part C of number 9, given the one acceleration. What's the other acceleration? Hopefully you got A and B. If not, look back to the Newton's third demonstration that we did in class about them both having the same force, because the Newton's third law, things like that. All right. And so we're going to do the part 3, part C, excuse me, and this is number 9. All right, so for this one, actually, I need 2 force diagrams. We have the brother, and we have the sister. She's a lot smaller than the brother, right? 15 kilograms, and he's 66. So I might even actually write that right in here, 15 kilograms and 66 kilograms. I could always write that as, like M1 and M2. So my correct force diagram would have a weight down, normal force up, and there's a force on the brother due to the sister, and on the sister we have her weight. I'm going to call that FGS. And then force on the sister due to the brother. Yeah, because we don't want people to think that the normal force or the weight of those are the same, right? Because they each have different weights. different normal forces in this case. That would be a full credit force diagram for this problem. Now the nice thing is we want to know, oh wait a minute, I forgot parts. Okay. It would have to be accelerating in this direction, these two different directions. I made all sorts of mistakes. Brother, sister. Because if I look, if they're standing on the ice, are they accelerating up or down? If they're just standing on the ice, what do you think? All right, well, think about that one for a little bit. Maybe we'll come back to it. But horizontally, they only have one force on each of them. Therefore, that force by itself, unless it's zero, which wouldn't make sense, is going to cause them to accelerate horizontally. Whenever you have a net force or a total force, you accelerate. And in this case, there's only one horizontal force on each of them. So they must be accelerating in that direction. So where I'm going to go from here is I'm going to do the brother and the sister. And I know from doing the multiple choices that the force on the brother from the sister equals the force on the sister from the brother. I also know that from Newton's third law, hopefully. All right? So, do the brother first. Sum of the forces, x equals MAX. And this is just the brother. The only force on him is F ds. Then I'd have the mass of the brother and the acceleration of the brother. That'll be good. And then for the sister, some of the forces in the x again. No, you'll see in a minute. We'll see in a minute. The only force on her is the force SB. That equals the mass of the sister, the inertia of the sister, times the acceleration of the sister. And I get down to this point and I say, okay, well, I know those two masses. I don't know the forces. I know one of the accelerations, but I don't know the other one. So I'm kind of, looks like I'm at an impasse. But I remember this fact, right? From Newton's third law, those are equal. And so I can say that the mass of the inertia of the brother times the acceleration of the brother equals the inertia of the sister times the acceleration of the sister. Right? Because those two forces are equal. Magnitudes of them. And now I can substitute in. For me, this is 66 kilograms. I don't know the acceleration of the brother. I think that's what I'm looking for, though, right? Let's see. This acceleration is this. What's the brother's? So then I can substitute also in for the mass of the sister and my acceleration for the sister. And the only variable I'm left with is acceleration of the brother. Nicole, that was what's interesting? Newton's third law. Okay. Sure? Okay. And then mathematically, I just rearrange these. A darn algebra again. I'm just dividing both sides by that 66 kilograms. see, now it's time to check. Parentheses, 15 times 0.6, close the parentheses, divided by 66. I get 5.909, so 0.591. 0.591 meters per second squared. Let's see, before I even bother with that, let's see if it makes sense. She's got a lower inertia, and this acceleration of 2.5. He's got a much higher, like 4 times higher or more inertia, and so he's going to accelerate a lot less. He's resisting it a lot more. Okay, so at least it seems like it's in the ballpark. Let's see if I got it right. Yeah, let me make sure that I didn't mess up there.